In this video, we'll look at an improvement to Euler's method called the midpoint method. After studying this video, you should be able to understand the midpoint method, analyze the error behavior of the midpoint method, and implement the midpoint method in MATLAB. Before we talk about the midpoint method, I want to talk a little bit about the general idea of one-step methods. Euler's method is an example of a one-step method. It's called a one-step method because we're stepping from some yi to yi plus 1. So we're going across one h, or one time step. These methods are also called Runge-Kutta methods. And Runge-Kutta describes a generalized approach to developing the one-step methods, and we'll look at that in a future video. All of the one-step methods can be written in the general form where yi plus 1 is equal to yi plus phi times h, where we'll call phi the increment function. And it may be one or more mathematical equations to determine how we estimate the slope of the function from one step to the next. So recall Euler's method, yi plus 1 is equal to yi plus f of ti yi times h. This would be our increment function phi, and if you recall, the general formulation of an initial value problem for Euler's method was dy dt is equal to f at t and y. All we're doing with phi is that is dy dt, or the slope of the solution y calculated at the ith time step. So the midpoint method that we'll look at next just gives us an alternative approach to calculating that increment function. So let's look at the midpoint method. The basic concept here is to estimate the slope at the midpoint of the interval and use this to extrapolate to the next time step. So if we are looking at a point along a differential equation, and this is our exact solution, and we want to step from ti to ti plus 1, the first thing we'll do is we will define that midpoint as ti plus 1/2. And what we'll do is take our value at ti and first get a value here that we'll call yi plus 1/2, and that's at ti plus 1/2. So this is at the midpoint of the interval. And we'll get that value simply using Euler's method to predict that value. So the first step here is to say yi plus 1/2 is equal to yi plus f evaluated at ti and yi times h over 2. And that's h over 2 again because we're only going to half the interval. Then when we get to that point at half the interval, we'll then take the slope at that midpoint. And we can get the slope at that midpoint. So here's that slope right here at that midpoint would be f at t plus h over 2 and yi plus 1/2. So we'll take that slope at the midpoint and then use that slope to extrapolate our next point from yi. So we'll take that same slope here and use that slope. There's a parallel line there. Sorry. We'll use that slope. I'll draw a parallel line that gets us all the way to ti plus 1. And so now we're at ti plus 1 and yi plus 1. So what we've done there is calculated yi plus 1 as yi again plus, now we're evaluating our slope by using that function that describes our differential equation at ti plus h over 2, or ti plus 1/2, and yi plus 1/2, and then times h. So the key difference here is our slope is calculated at an it's estimated using Euler's method to get yi plus 1/2 at an estimated midpoint of the interval. So these two equations together give us the algorithm for the midpoint method. So let's look at the truncation error behavior of the midpoint method. Recall the error behavior of Euler's method. It was first order accurate, or the local truncation error was order h squared because we truncated the second order term from the Taylor series, and global truncation error, as that accumulated, became first order accurate, order h. If we look at Euler's method algorithm, we can see, if you recall, that this is dy dt. If we solve for dy dt, we get something that looks like yi plus 1 minus yi over h. And recall that looks like a forward finite difference calculation, and those were also order h. So this is another way to get a handle on the error of Euler's method. We're using a first order derivative approximation, in a sense, to estimate dy dt, or to use dy dt to find yi plus 1, and that results in a first order accurate method. The midpoint method is more accurate than Euler's method because it uses a slope estimate at the midpoint of the interval. So let's look at that. Let's get an analogous finite difference approach. So here we would get dy dt all at I plus 1/2 is equal to yi plus 1 minus yi over h. And notice that I plus 1/2 is at the midpoint, it's the middle of I plus 1 and I. So what we have now for this analogy is more like a centered finite difference derivative approximation for that increment function. And since it's a centered finite difference derivative approximation, if you recall from our earlier discussion of numerical differentiation, that centered finite difference approximation is going to be order h squared, or second order accurate, and that would be a good approximation of the global truncation error behavior of the midpoint method, which then leads us to conclude that the local truncation error would be third order. So the local error is third order accurate, and the global error is second order accurate. And again, the main reason we got there is just looking at the formulation of the midpoint method as a finite difference derivative approximation, and recognizing, since we're taking the derivative at the midpoint between yi plus 1 and yi, that it looks like a centered finite difference derivative. So let's look at implementation of the midpoint method. So we have two equations to implement the midpoint method. First, we need to use Euler's method for a h over 2 time step to predict y at the midpoint, and then we'll use the midpoint method to predict yi plus 1. And so here's an excerpt from the M file midpointode.m. included with this video. Just the part, I've skipped all of the input to the function, which are very similar to the Euler.m function. And this is for a single ordinary differential equation. Also note this is only applicable as we've set it up so far for initial value problems. So we'll go to the main iteration to implement the calculation. So the first thing that we do at each time step in the iteration is calculate that predicted y value, which I've just called y mid. So again, we're calculating that using Euler's method and a time step of h over 2. Then we'll use that predicted midpoint, y mid, along with the time value, ti plus h over 2, to get that slope at the midpoint, and use the midpoint method now for the entire interval over h to get yi plus 1. And you can easily expand this for a system of ODEs by using a set of nested for loops like I discussed in the system of ODEs video, and I'll let you do that this week. And that concludes this video on the midpoint method.